Earlier, we mentioned that the number of passengers and the amount of baggage you carry plays a role in your Skyhawk's performance. It's time now for a more detailed look at managing the weight in your Skyhawk. And I keep telling this guy, lift with your legs. It's a really good way to hurt yourself. Before getting serious about weight and balance, it would help if you equipped yourself with a simple calculator. A cheap one will be just fine because all you need to do is add, subtract, multiply, and divide. My calculator happens to be solar powered, which means I have to go to the beach to do my taxes every year. And the IRS hates that when you get cocoa butter on your W-2s because they're stuck in some drafty, dank building. Now, you should remember that the maximum takeoff weight for your Skyhawk is 2,450 pounds. That's the maximum takeoff weight for this particular Skyhawk. That's the weight upon which the engineers based their safety factor calculations. But the total weight isn't the whole story. It's extremely important how that weight is distributed. You know instinctively that even if your Skyhawk weighs, say, only 2,400 pounds, if 400 of those pounds are a couple of anvils in the aft baggage compartment, it's not a good thing. Particularly if the good old Skyhawk is resting on its tail tie-down ring. You're not going to get very good performance in that case. The point in an airplane about which the weight of the airplane is balanced is called the center of gravity, or abbreviated, we use CG. It can be defined as the point where the airplane would balance if it were placed on a fulcrum. First, let's start out with a demonstration of how easy it is to understand weight and balance. Remember when you were a little kid and you were playing on a teeter-totter with some bigger kid? Well, if you moved way out to the end of the board and the big guy scooted in toward the pivot point, you would eventually find a place where you both could lift your feet off the ground while the board stayed perfectly balanced. That's because you moved the weight until the center of gravity was right over the pivot point. At that time, if you had measured from the pivot point to where you each sat and multiplied each of your respective weights by those respective distances, the products would have been equal. And to make it simpler, and in no way gender specific, little guy times long distance equals big guy times short distance. The distance in this case is called the arm, and the product of weight times arm equals moment. And you'll be hearing these terms throughout this lesson and the next lesson too. This equality of moments principle can be turned around and used to find the location of the center of gravity in any system of weights and distances, including an airplane and its load, which is very helpful for us in this case. The formula that defines this is the total moment divided by the total weight equals the center of gravity, or CG. The beauty of this is that it doesn't matter where you start measuring the length of the arms as long as you measure all of them from the same place. The location of the CG is determined by the distance from that measuring point. That point even has a name. It's called the datum point, or more simply, datum. Alrighty, folks, let's try a practical example. We'll put some weights on a beam and see where it will balance. The beam in our example is 9 feet long, and we'll be measuring from the left end, going over to the right, and that's your 9th foot over there. Now, it's a lot easier if you stay organized working weight and balance problems. So let's make a table that you can use for any problem. In the far left column, we'll have the item with which you're working. And then we'll have the column for weight, and then we'll have the arm, and the moment equals the product of the weight times its respective arm. So weight A has an arm of 2 feet, so we'll multiply 100 times 2, or a total of 200. Weight B's arm is 4 feet, that's 400, and weight C is 9 feet, or 900. The total, the sum of the moments right here, 1,500. Then using our formula, the total moments divided by the total weight equals your center of gravity. So we'll take 1,500, that's our total moment, divided by 300, our total weight, and bingo, the center of gravity is 5 feet from the datum, which we said was where? It's at the left end of the board. Notice that. Just like the kids on the teeter-totter, the moments on either side of the balance point are equal as well. You can measure in either direction from the balance point. So let's do it this way. Let's take 4 units, 1, 2, 3, 4 times 100 equals 400 to the right of our balance point. And let's go to the other side. 1 times 100 equals 100, and 1, 2, 3 units times 100 equals 300. Those total to 400 also. Voila! Would it have made any difference if you had a datum somewhere else? Nope. You just have to remember that the location of the CG is expressed as the distance from that datum point. Let's prove this point. Let's recalculate the last example using a different datum point, say underneath weight B right here. We'll call that spot 0 and identify the distances on the new scale as negative to the left and positive to the right. We'll leave the old labels on the diagram to compare the old and the new results. All right, let's create another table to keep it all sorted out. Weight A has an arm of -2, so that will be -200. Weight B has an arm of 0, so that's going to be 100 times 0, or 0. And finally, weight C has an arm of 5, and 500 is the moment in this case. So 200 from 500 equals 300. Applying the formula, total moment divided by total weight equals center of gravity. 300 divided by 300, the center of gravity equals 1 foot from the datum, and that's +1. Well, as you can see, that points the center of gravity and places it right here at the same location it was in our first example. It would have given this result if you had used a datum point that wasn't even touching this board. The CG in that case would have been identified as a distance from that new datum point off the end of the board somewhere. Just remember, your final result from that formula equals the distance from the datum point. So now, you know the principles of weight and balance, and in the next lesson, you'll apply those to your Skyhawk so you can keep it in the envelope for safe flight.